All right, so our last section we're going to take a look at for this week is on volume. Okay, so as we just said, volume is basically how much stuff you could fit inside the object. Versus surface area is if you were building the object, how much material would you need to make the walls? Okay, that's the difference. Okay, so the volume of a solid, as I said, the way we're going to measure it is the number of cubic units, cubic feet, cubic inches that fit inside the shape. Okay, so here's some examples of units you might see in this class. Cubic centimeters, cubic inches, and cubic feet. Okay, some people say like feet cubed. You could say it that way, but usually you say like cubic feet. Just like if you were buying flooring for a room, you'd say, I need 20 square feet. Usually you wouldn't say I need 20 feet squared of, tile or something. 20 square feet. All right, but that's okay. All right, so we're going to start out with a few things that are facts we're not going to prove. I'm just going to give them to you. Basically, formulas we're going to use. Okay, first one is for the volume of a cube. Does anybody already know how you find volume of a cube? Yep. Yeah, it's length times width times height. And what's special about the length, width, and height in a cube? All the same. So basically, you could just say the volume of a cube is the length of a side cubed. Side cubed. Now the formula Connor gave us that's also fine. Generally, when we talk about a prism, maybe in the shape of like a Kleenex box or like a piece of styrofoam that's like this, the length, width, and height might all be different dimensions. And that's when we'd use that. Okay, so that's the volume of a cube. V equals S cubed. And that's on your MCAS reference sheet. Okay, another fact about volume might be kind of common sense to most people, but it says if two polyhedra are congruent, they have the same volume. So basically, we have two shapes that are identical, they're each going to hold the same amount of stuff. It's almost common sense. How about the other way around? You think this would be true the other way around? If two polyhedra have the same volume, then they're congruent. No. It definitely wouldn't be true the other way around. If you have two containers that hold the same amount of volume, do the containers have to be identical? No. Maybe one of them is like a wider container, not as tall, or one of them is a very tall, narrow container. Okay, so this isn't true the other way around. Two things hold the same amount of stuff. They don't have to be the same exact shape. But if they are the same exact shape, then they will have the same volume. Okay, and this part kind of ties in with what I was saying earlier about stacking shapes together. If you've got a shape that maybe is a cylinder with a cone stacked on top, okay, or a cube with a pyramid on top, if you want to find the volume of the whole shape, all you have to find is the volume of each individual part and add them up. Okay, so the volume of a 3D shape is the sum of all the individual volumes of all the parts that don't overlap. Okay, any questions on those three basic ideas? Volume of a cube, volume congruence postulate, volume addition postulate. So these are all basic facts that we're going to use as we kind of go through this section. So here's a box. This diagram is in your book. It's on page 743. It's a little clearer in your book. But it says the box shown below is 5 units long, 3 units wide, 4 units high. Basically, we want to know how many cubes that are 1 by 1 by 1. How many could you stack inside that box? Okay. Well, basically, if you can tell me how many of these cubes fit in the box. That's the volume of the box. However many cubes fit in it that are 1 by 1 by 1. So this approach is very, very nice to do on Prism, where all the sides are integer lengths. Because you can always fit in a nice number of boxes. It'll be full right to the top. There won't be any left over. If you have decimal lengths, then it's kind of hard to do this idea. This is kind of something you could do in like 2nd or 3rd grade. You have to stack the boxes. And, you know what I mean? Doesn't work so well with a cylinder because then the walls are curved. You can put boxes in, but you're going to have a lot of space left over. Okay. All right. Right, so we're going to basically find the volume of the box. Can anybody tell how many cubes are in this bottom row? Kind of this bottom layer? Yeah?
12.
12? Let's see. So we got 5 across the front, and it's 3 deep.
15.
So 15. Okay, so kind of a quick way to add these up. The bottom layer has 15 cubes. And then how many of those layers could we stack on top of each other to get it to the top of the box? Jim? Yeah? 4, yeah. If you stack 4 of those layers, because the box is 4 units high, so we'll times that by 4 layers. So we get 60 cubes. Now we just had a formula right here. Tells us how to find the volume of a cube. Volume of a cube is length times width times height, or side cube. So in this case, 1 times 1 times 1. Okay, so each cube has volume of 1 cubic. Did they say what the units were? Just units. All right, I thought they said centimeters. When they don't say a unit, you can just put U cubed, units cubed. So each cube has a volume of 1 cubic unit. It's 1 by 1 by 1. And you have 60 of them. So what's the volume of this prism? Jacob? How many cubes fit in that box?
60 cubes.
What's the volume of each cube?
1 unit is cubed.
Yep. So if you have 60 cubes and each one of them has a volume of 1 cubic unit,
60 units cubed.
total volume is 60 cubic units. Yep. Total volume, 60 cubic units. Any question on that? Okay, as we kind of go on through this, we're not going to take the approach of figuring out how many cubes could you stack inside a box each time. We're generally going to use formulas, especially when we get to like a cylinder. Okay? If you use cubes that are 1 by 1 by 1, you have a lot of leftover space. What do you think would give you a more accurate measurement of the volume? If I took and made each cube smaller and tried stacking smaller cubes in the cylinder, or if I made the cubes bigger? Which one would give me less, a more accurate representation? There'd be less leftover space. Yeah?
Smaller.
Smaller. Yeah, smaller. Okay, think of, think if you had a box, okay, and you wanted to fill it with like spheres. Okay? Well, spheres don't stack nicely in a square box. Right? If you stack it full, you're going to have a lot of gaps and leftover space. But if you had smaller and smaller and smaller spheres, then the leftover space would be smaller and smaller. Okay? Picture stacking like bowling balls in a box versus tiny marbles. Okay? The marbles are going to be a lot more compact. Right? So if we wanted to try this approach, something even smaller, we could use like sand. Okay? Grains of sand are even smaller. If you pour grains of sand in something, it'll pretty much fill every space in the 3D shape without much left over. Okay? And then if you had it full of sand, you could take all that sand, you could dump it out, weigh it, and you can figure out the volume of your object. Okay? In fact, that's how some people they measure different things. Like you can measure your weight by stepping on a scale. One way to measure body fat is called hydrostatic weighting. Basically, you can go in water and they could measure, they fill like a tank full of water, and then when you get in, all the water that comes out of the tank, because you're getting in, they can measure how much water came out and figure out different things. It's a pretty accurate way to measure stuff about the human body. All right, so volume, it's used in all kinds of different places. All right, let's look at volume of a prism. This formula applies to every single prism you ever come across. What changes every time is B. Okay, so V is volume, H is going to be height. What do you think B is? It's the same thing it was when we did surface area.
Base.
Area of the base, right. Okay, and that's the part that can be tricky. Okay, if your base is a hexagon, you're going to know the formula for an area of a hexagon. If your base is a triangle, you need that formula. Okay, so that's the volume of every prism. In fact, you can even use this formula for the volume of a cylinder. Area of the base times the height. Except in a cylinder, I can tell you what the shape of the base always is. It's not like a prism. It doesn't change. A cylinder is always a circle base. A prism could be any polygon. So since the formulas are so similar, I'm just going to give you both of them right now. Okay, so it starts out the same. Volume equals base times height. But we can figure out what the base is, because in a cylinder, I just said it never changes. The shape of a base is a circle. What's the area of a circle?
Circumference? Oh, no.
Not the circumference, I want the area.
Is that 2 pi r?
2 pi r?
That's the circumference of pi r squared.
Yeah, 2 pi r is the circumference, pi r squared. That's the area of the base times the height. Okay, so we're just filling in a specific area of base formula because it never changes for a cylinder. So in this case, r is your radius of the base. Okay, but I just try to remember this formula right here, V equals BH. Just remember my initials, BH. The area of the base times the height. Okay, any questions on those two formulas? And that's it. It's the only two formulas you need to know today. Okay. So in general, what they'll do in these formulas is they'll give you a couple things. Okay, they might give you the radius and the height and say find the volume. Or they might give you the volume and the height of the cylinder and say what would be the radius. Or if they were even tricky, they might say what's the diameter. So you have to remember once you find the radius to double it. Okay? But they'll always give you every variable you need except one. Another thing we can do with volume, if we have time, we'll look at it maybe later on, is I could say, suppose I had a sphere and the volume was 200 cubic inches. I'm going to melt that sphere down. Okay, it's metal. I'm going to melt it down and I'm going to turn it into a cylinder.
Why not butter?
Okay, we could use butter. So we're going to melt that down and then we're going to put it in a mold. We're going to turn it into a cylinder and I will tell you that the cylinder has a radius of 3 inches. If you melt that sphere down into a cylinder with a radius of 3, how high would it be? Okay? And the idea there is the amount of stuff you have when you melt it down, we assume we don't spill any, the volume stays the same. We're just melting it and turning it into a different shape, but it's the same volume. Right? So we can use that idea to figure out problems as well, which eventually we'll try. All right, so we're going to try two problems. First one is about a prism. Next one's about a right cylinder. Okay. Can anybody be more specific? What kind of prism is that? Okay, we know it's a prism because we have two congruent bases that are parallel.
It's a triangular prism.
So Anna said the answer, but she didn't say it. She whispered
She
it.
did say Alana? Yeah, if she said that, then that was right. Triangular prism. Is the triangular prism on its base, the way I drew it?
Yeah.
Yeah, it's on its base. It's either going to be on this side or this side. Those are the bases. If you were to turn it over and lay it on the rectangular side, that's not its base. That might be the most likely side if you just took the prism and dropped it that it fell on, because it's the biggest side, but that's not the base. All right, so it says find the volume. Okay, let's start with our formula. What's the formula for volume of any prism? Katrina? What about the base?
The area.
Area of the base, good. Times the height. Okay, so the shape of my base here is a triangle. Okay, shape of my base is a triangle. What's the formula for the area of a triangle? Just write that down. Melissa? Yep, it's 1/2 the length of the base times the height. So when I want length of base, I'll try to use a lowercase b. Talking about the area of a base, I'll try to use a capital. All right. And now, remember, this is a 90-degree angle. That's the whole key that helps us do this problem. If that wasn't a 90, we'd be stuck a little bit. Okay, so let's find the area of my triangle, which is the area of my base of the prism. Okay, so it's 1/2. Luke, what's the length of my base here? Can you just focus on the triangle?
The length of the height, technically, or the entire length?
Well, you could interchange the b and the h, and it really wouldn't make a difference. You could look at it either way.
I don't know. 2? Would that be the length? I don't know.
2 is the height of the prism.
4.
That's the distance between the two bases.
It's 4 then. I don't know.
Okay, so the length of the base is 4. And what's the height of the base?
Ew, did I just say that?
I thought you gave me the length of the base.
Oh, 2 then. I thought you said they're interchangeable. You could just do 2 and 4 or 4 and 2.
All right, let me redraw it and show you what two numbers we should focus on and what number we need to forget about for now. Okay, so all we're doing is focusing on the triangle. Okay? So we're focusing on this. Okay? It's drawn in perspective, so it doesn't look like that's a 90-degree angle. Okay? Let me draw it like you were looking at it from the top. Okay? It would look something like this. Okay? That's the side in red. If you were looking straight down from the top, okay, you wouldn't even see the sides of it. You can just see the triangle. Okay. This side is 3. That side's 4. All right, so the area of a triangle is 1/2. Luke said the length of the base was 4. What's the height of the triangle?
3.
3. Yep. Okay, so the 2 doesn't really have anything to do with the base. It has to do with how far apart the bases are, but it's not the height of the base. It's the distance between them. All right, so we can do this out. 1/2 of 4 is 2 times 3 is 6. That's the area of my base, 6. Okay, so now we can find the volume. Area of the base times the height. That's the distance between the bases. So the volume here is 12 cubic centimeters. That's how much stuff would fit inside that prism if you were to fill it up. Okay, any questions on how we did that? Okay, so sometimes if it's helpful, take your base and draw it separate. So you don't have to look at it as part of the picture, and try to draw it the way it would look if you were looking at it straight on, right? Not looking at it from like an angle. Okay? That's why they'll always mark it as a 90, because it's not going to look like a 90 with the perspective. Okay, so here's a cylinder. Just to kind of get a sense of three-dimensional drawing, if you were looking at a cylinder and it looked like this to you, how would you be looking at the cylinder? Like, what would be your view? Con?
pieces? Using the top and the bottom?
Like, would I be looking up at the cylinder? Or would I kind of be looking down at it? Or would I be looking straight down on top of it?
Depends.
Based on this view. There's only one answer
You're
based on
looking
that.
at the top.
Straight down, like looking straight at the top?
Angled.
Yeah, you're looking at it kind of angled. All right, so if I had a cylinder and I could stand it up, you know, something like that, I'd be looking kind of down on it a little bit because I can see the top, but I can also see the sides. If I was looking straight down, all I would see is a circle. Okay? All right, so let's start with our formula for volume of the cylinder. Sarah, what's the formula for volume of a cylinder?
Base times height.
Perfect. Area of the base times the height. Now for a cylinder, the base is always the same. Morgan, what's the shape of a base in a cylinder? Yep, it's always a circle. And can someone remind me, what's the area of a circle? I think Denver said it earlier.
R squared.
Good. Pi r squared times h. So when you look at your diagram, hopefully they gave you r and h. In this case, they did. Okay, Rose, what's r in this case?
8,
Yeah, radius is 8. And how about my height?
15.
15. Another thing you want to be careful of, this would be really tricky if they did it, if they gave you, say, the height in feet and the radius in inches. You got to make sure that everything is in the same units. Another thing they could do to you would be something like draw a line all the way across, give you the diameter. Remember, the formula needs the radius, not the diameter. So there's all kinds of little things they could do to trip you up a little bit. All right, so we got pi times 64 times 16. Okay, let's just leave our answer in terms of pi. So it's 960 pi. Right, and that's square, cubic inches. Okay, if they wanted a decimal, do 960 times 3.14. It's going to be probably a little under 3,000. Denver?
What about pi makes it work for all this circle stuff?
What about pi what?
Like why does it work for this circle stuff? Like,
Oh, kind of where does the pi come from?
yeah.
That's a good question. So pi, obviously we have this number, I used to have it up in front of the room here, 3.14, and it kind of just keeps going on. There's all kinds of different explanations about where it comes from. When I took some history of math classes, we kind of studied where it came from. I honestly don't remember the exact explanation of where pi came from. But there's different ways people tried to approximate it. Throughout, I remember it got more and more accurate as time went on. For a while, people just used like 3.1 because that's as good as they could get. One way you could kind of do it yourself, kind of experimentally with like a piece of string, is if it's kind of cheating because you already know the formula. But if you basically did this, you should get pi. So if you take any circle, take a piece of string, measure the circumference of that circle with a piece of string, and then take a ruler or tape measure, whatever you need, and measure the diameter straight across the circle, and then divide the two numbers you get. You should get something pretty close to pi, 3.14. Right? But again, why exactly you get this 3.14 number goes back into the history of pi a little bit that I don't remember well. But I do know some people, I think in like elementary school, they do this as kind of an experiment. They give students different size circles, and they give them a piece of string, and they have them measure each circle with a piece of string, get the circumference, then measure each diameter, and see what number they seem to get. And most people get pretty close to pi each time. So it's kind of an interactive way for little kids to see kind of where it comes from. But it doesn't mathematically explain why you're getting pi. Yeah. So, but if we have time to meet at the end of class, we can pull up the history of pi or where that came from. Yeah. But yeah, anytime you have a curved object, like spherical, cylinder, cone, you always have a pi in there somewhere. You never really use pi when you have prisms or pyramids. It just doesn't come up. We can take a look at the end of class if we have some time on that. Okay, so here's another principle. This idea is a little bit more advanced. But basically it says that if two solids have the same height, okay, so you measure two solids, same height, and then they have the same cross-sectional area at every level. Okay? So you take your two solids, say you go 2 inches down, you slice one of your objects. Go 2 inches down, slice it again. Look at the shape when you slice it. Measure its area. If it comes out the same, no matter what level you slice the object at, the two shapes would have the same volume. All right, so there's a picture of that on page 744. All right, so if you have two 3D shapes and they have the same height, and you slice those two, put them on the table, slice those two shapes straight across, look at the area of the cross section. If it comes out the same, no matter where you slice it, when you compare the two areas, those two shapes would always have the same volume. Okay, and what this principle basically allows us to do is find the volume of oblique prisms and cylinders. Prisms and cylinders that are kind of slanted. The point of this principle is it doesn't matter if you take a cylinder and you slant it. We can still work with it the same way as if it were upright instead of slanted. Let's see if I have a picture of, do I have anything slanted? Just seeing if I do. No. Okay, so our book doesn't spend a lot of time on it. So we're not going to really do too many examples with it. Okay, but if you look at the example in the book, they've got a rectangular prism, and then they take that prism and they slant it. I don't know if you can see it. They take that prism and then they slant it. So what they're showing is if you slant it and the cross-sectional areas come out the same for each shape, they have the same volume. So we could work with shapes that are oblique. Okay, so here's one they're kind of switching up what they're giving you a little bit. You know the volume already. I want to know how long each side would be. Okay, before we even do any kind of math here, what do you think we need to write down?
Formula.
Yeah, we need a formula. Okay, so to figure out your formula, look at the shape you're using, look at the information they're giving you, and then find a formula that relates this information and this shape. So we're dealing with volume, and the shape is a cube. So let's write down the formula for a volume of a cube. What's our formula for the volume of a cube?
Length times width times height.
Okay, we can do length times width times height, or for a cube, what's special about length, width, and height? Yeah,
It's all the same.
they're all the same. So volume equals length of side cubed. Okay, Marquise, in this formula, what do I already know? Yeah, I know the volume. So fill in 100 for volume. And we're going to find the length of the side. How do I do that? You get S by itself there.
You divide
You find the cube root of 100.
a cube root.
Yeah, we're going to do a cube root. Okay, we're going to do a cube root. The only way to get rid of an exponent of 3 is to do the opposite of an exponent of 3, which is a cube root. Cube root, cube, and cancel. Okay, this is something I want to make sure people know how to type in on a calculator. This calculator, you type it in pretty much the same way as the ones I give you for a test. Okay, first thing you do is you type in the type of root you want, which in this case is a cube root. Okay, and then there's usually a button. You don't get to it by pressing math, but there's a button on the calculator that looks just like that. It's got a little X, and then it's got a little root symbol. And that X basically is going to get changed to whatever number I just typed in. So I typed in a 3. So if I press the 5th option down, see how I just made it a cube root? Now my calculator, it's not going to make it look nice and pretty like that. It's going to end up looking like this. It's just going to stick the 3 in front, because my scientific calculators can't write the 3 small like that. And now we just type in what we want. Cube root of 100 means each side is about 4.64. Okay, about 4.64. What should be my label on that? 4.64. Wow. Yep. Feet. Just feet. Right. Questions on that? Okay, cubic feet, I do know that volume unit is used quite a bit. Like for water departments, when I get my bill every 3 months, they measure it in units. And every unit of water is 100 cubic feet. So if I use 6 units of water, okay, in 3 months, that would mean I use 600 cubic feet of water. If I use 8 units, it's 800 cubic feet. And I think if you look at your water meters on your house, there's like, it almost looks like an odometer, like an old-fashioned one from a car. It's got the little wheels that kind of roll in it. I'm pretty sure that measures in cubic feet, your water usage. And a cubic foot is actually quite a bit of water. So imagine a box that's a foot by a foot by a foot and filled with water. How many gallons? Picture a gallon of milk. Okay? Then picture a box that's a foot by a foot by a foot. How many gallons of milk? They wouldn't fit perfect. How many do you think you could fit in there? 3? So you have a box foot by a foot by a foot. Maybe you could fit in 3 gallons of milk, 4 gallons. It's actually closer to 7. I know it seems kind of weird, but if you had a box of foot by a foot by a foot, you could dump between 7 and 8 gallons into it. Okay, somewhere around there. So a cubic foot is quite a bit of water. Okay. Anybody know how heavy that would be? It's kind of a different question.
60 pounds?
Yeah, it'd be pretty heavy. If you had a box, that wouldn't be a very big box, but it'd be pretty heavy. Gallon of milk is probably about 7 pounds, somewhere around there. So if you had 7 gallons, each one was 7 pounds, it'd be about 50 pounds. Right, so it's just kind of a couple things you can think about, not really related to volume, but they can be. Like if you know how heavy, like let's say you had 50 pounds of water, and you know the density of water, you could figure out the volume. Right? So if you know how heavy the stuff is you have, and you know how dense it is, you could figure out the volume of it. In fact, you've probably done that in like chemistry or maybe even biology. Density, mass, and volume. You can make like a little triangle out of it, and you can figure them out. All right, so let's try finding the volume of this cylinder. Actually, they give us the volume. Let's try finding the radius. So try the density. Okay, anyone give me my formula for the volume of the cylinder? Try to give me the specific version, not just the area of the base times the height.
Volume equals pi r squared times height.
Yep, pi r squared times height. Okay. They're giving me volume. What about that 12?
Height.
Yep, that's the height. The only thing I'm going to be missing is the radius, which they called x, we could call it r. Just remember what we're solving for. Let's fill in the volume. Let's change pi to 3.14. Just round it off. Okay, whether you round pi to 3.14 or use the pi button, kind of depends on what the application is. Okay, if you are making very, very precise parts, say you're making parts for an engine or machining things, I don't think rounding to the nearest hundredth is going to be good enough. Probably want to go to the nearest thousandth or maybe even 10,000ths, okay, to be accurate enough. But for our purpose, I think this is fine. So, we're going to take 4561, and how are we going to get the 3.14 and the 12, both on the other side? Yeah, we're going to divide by both of them. So if you want, do both in one step. Divide by 3.14 and divide by 12. And now, what's my last step to get rid of this exponent of 2? Square root. Now, at some point, if they want a decimal, we got to type this in. So I've avoided typing it in as long as I really can. All right, let's type it in. Take 4561. Divide by 3.14. Then you can take that answer and just divide it by 12. It's the same thing. Now take that answer and take the square root of it. Okay. And what I can do, so I don't have to type in 121.0456, I can just take the square root of the last answer that was on the screen. You can do that on my calculator as well. Okay, so it comes out to almost exactly 11. So it's 11.0 meters.
Will it work?
It'll work if I use the right thing. Does anybody know what's the significance of putting down 11.0 versus 11?
It shows that there's actually more to the number.
No.
Yeah, well, it shows that there is more to the number, and it shows that I know the accuracy to this place. Okay? In fact, depending on how you round it in chemistry, you might have used significant figures. You ever used those before? No one's ever used them, or
No.
you have used them? Yeah. Significant figures, they're kind of rules for where you round things off. In geometry and algebra, we don't use them as much. Okay, but you can. All right, so last problem we'll look at is this object. Okay? So we've got a concrete block. Okay? And I'm telling you how much concrete weighs per cubic foot. All right? So it's almost kind of like the density in a way. It's how much a cubic foot of it weighs. I want to find the weight of this block shown. You don't have to be specific with numbers, but can anybody give me the general approach? What would you have to do first, kind of step by step, to find the weight of this concrete block? Yep.
Find the area or find the volume of the concrete itself.
Like the whole block?
The whole block, and then subtract it.
Step one, we'll find the volume of the entire block. Let's ignore the holes. Okay, ignore the two holes that are in it. So find the volume of the whole block, ignore the holes for now. Then what would you do? After you find the volume of the whole block. We've overestimated a little bit at this point. Yep.
Find the volume of the whole and subtract.
Yep, so get the volume of the whole block.
No,
Subtract.
the whole.
Oh, the whole, not the whole block. Just so find volume of the whole. And how many holes are there?
2.
2, and they're identical. So find the volume of the whole. Okay, double it. That's supposed to be Just having trouble writing today. So find the volume of the hole, double it, and then subtract that from step 1. So subtract this from what you got in step 1. Now that's only going to give us the volume of the block. They want the weight. So how would we, once we have the volume of that block, how would we get the weight? Any thoughts on that?
Oh, 150, I didn't say that 145 pounds.
Yep, we know that each cubic foot weighs 145 pounds.
Pretty heavy.
So if you had a cement block, foot by foot by foot, that's what they're saying it would weigh. So once we have our volume, how are we going to change that into weight?
Cubic feet.
You multiply the volume by the pounds.
Yeah. Once you have your volume, multiply by 145. So in other words, if we get a volume of 2 cubic feet, it would weigh 145 times 2. If we get a volume of 1.6 cubic feet, take 1.6 times 145, and that'll give us our weight. Okay, so let's go through and then see if we can do that. So last step is multiply 145 times the answer in step 2. Okay, let's find the volume of our prism. Volume, we'll call this the volume without the hole. Or, you know what, we can even say volume ignoring hole. Then we'll have to subtract the hole after. Okay, so we've got a prism. So it's going to be the area of the base times the height. Is this block on its base?
Yes.
Yeah. There's several ways with a prism. You could basically turn a prism any way, a rectangular prism, and it's always on its base. Right? So let's find the area of the base times the height. Let's start with the easy part. What's the height of that block?
0.66 feet.
Yep, 0.66 feet. Okay, now to find the area of the base, it's in the shape of a rectangle. Okay, what's the length of the base?
1.31 inches.
1.31
Feet.
feet? Okay. And Denver, what about the width of my base?
0.66.
Yep, 0.66. Okay, so my length, 1.31, width, 0.66. What do we do with those two numbers to find the area of the base? Luke?
To find the area of the base,
Yeah.
you multiply 13 by 0.66.
So your two options that we're using the numbers 1.31 and 0.66.
Yeah, 0.66. 1.31 times 0.66. I thought it was 13.
Good.
Don't crucify me.
Okay, so your area of your base is let's say 86. Okay, to get the area of the base, we've got our height. Now multiply them together. So we got 0.86 times 0.66. Now, is that an overestimate or underestimate of the actual volume?
Over?
Yeah, that's over. Because we found the volume pretending this was solid block. It's got 2 holes in it. Those 2 holes are going to take out probably a majority of the cement. Right? So we got 0.57 cubic feet. That's the volume ignoring the hole. Now, what's the shape of that hole?
Rectangle.
Well, it's a rectangular prism.
Yeah, the cross section of it, if you took the hole, it's square. But if you look at the whole thing, it's a rectangular prism. So now we're going to find the volume of the hole, which is another prism. Okay, let's find that. And remember how many holes we have? We've got 2. Okay, let's start with the area of the base. Okay, well, it's 0.33 and 0.39. Multiply those together. That's the area of your base. Okay, so 0.13. What's the height of the hole? They didn't mark that again.
0.66.
It's still 0.66. It's the height of the block. Okay, 0.66.
So we know it goes all the way through.
But we'll assume it goes all the way through, like a regular cinder block.
Yeah.
All right. So 0.13 times 0.66. That's the volume of the hole. 0.09. Okay, we're doing a lot of rounding, but that's okay. Just trying to get the idea of how to do the problem.
Gotta multiply that by 2 though, because 2 of them.
Right. So now we're going to double it. Right. So one of the holes is 0.09. The other hole is 0.09. Double it. It's 0.18. Okay, so the actual volume of this block is the volume of the entire block. Subtract out the hole.
18.
Yeah, 0.18. Does everyone see why we're going to double that?
Yeah. There's 2.
0.09. Okay, so let's see how much concrete we actually have. 0.57 minus 0.18. So it's 0.39, roughly, cubic feet. So now the whole goal here was how much does that weigh? Concrete weighs 145 pounds per cubic foot. So do we have more or less than 145 pounds? Less. We don't even have a cubic foot. We've only got, was it 0.39? So what are we going to do with the 0.39 and the 145?
Multiply them.
Yep. Good. So the weight it's 145 times 0.39. Okay, so let's see how much the cinder block weighs. Anybody know how much a cinder block really weighs? Anybody know if those dimensions they gave us were really accurate?
Probably not.
It seems accurate. 0.66, that's 2/3 of a foot, so that's 8 inches by 8 inches by
A cinder block weighs 40 pounds.
16. Is that a cinder block 8 by 8? Is that pretty much what it is?
Sounds.
Need a mason. You guys- So with all our rounding, we got about 56 and a half pounds.
I actually weigh 47. Way more than that.
56.6.
Bless you.
Okay. Any questions on that? Everyone feels okay finding volume of prisms and cylinders? Okay, it's pretty straightforward. All right, so I want to give you guys not quite as much time as yesterday, but you got about 10 and 12 minutes, okay, to get started. So the homework's on 746. I want you to try 10 to 19 all. Does that look a little fuzzy?
Yeah, it does. That's better.
Yeah, 10 to 19 all. 24 to 32, just even. 37, 39, 42, 46, 47. And don't forget, this homework's not due until June 1st. Okay, so I'm going to check it Monday, June 1st.
If you don't get that, I'll show you a hole.
Don't forget.